Hi everyone! In this video, I'm going to show you the solutions to the Class 7 Triangles, Polygons, and Trigonometry homework problems. So you remember from Class 7, we discussed area, similar triangles, polygons, and also some basics of trigonometry. So now we're going to solve the homework problems that use these concepts. So now let's start with the first problem. Points P and Q lie in a plane with P, Q equals 8. So we have P, 2 points P, and then we have another point Q, such that PQ equals 8, okay? So this is 8. So we're asked to find for how many locations are in this plane such that the triangle PQR is a right triangle with an area of 12 square units. Okay, so here's how I like to think about it. So if you have a triangle with an area of 24 square units, then let's call this height of the triangle H. Then we know that H divided by 2 is equal to 12. Or that H is equal to 3, right? Okay, so now we know the height of this triangle is 3. Okay, so if we know that the height of this triangle is 3, now what other information do we know? We know that PQR is a right triangle. And what does it mean for a triangle to be right? Well, for a triangle to be right, exactly one of its angles has to be a right angle. So now let's look at the different possibilities for R such that PQR will be a right triangle. So the first possibility is that RPQ is equal to 90 degrees. So if RPQ is equal to 90 degrees, there's only two possibilities. Let me just draw them out so you can see what they are. So the two possibilities are RPQ is 90 degrees are just this triangle. This can be R here. Because if this is R, then this is going to be 90 degrees, and then this will be a right triangle here. And then R can also be on the other side here. So R can also be here. And then PQR will again be a right triangle. So as you can see here, that R has these two possibilities here in which RPQ is 90 degrees. So these are the possibilities for RPQ is 90 degrees. Now, there's also other angles can also be 90 degrees. The next case is PQR can be 90 degrees. Okay, so if PQR is 90 degrees, then what are the possibilities? Well, the possibilities are simply equal to, you can have this angle be 90 here, and this angle be 90 here on the other side. So this will be 90, and this will be 90. So as you can see, these are two more 90-degree angles and two more triangles added to our count. Now, what is the last case? The last case is PRQ. And if PRQ is equal to 90, now what are the possibilities? Well, now let me just erase these because we've already counted for them. So we've already added 4 to our count. 2 plus 2. So now, the last case is if RPQ is 90 degrees. Okay, so if RPQ is 90 degrees, then we can see that the possibilities for R can be something like here. If PRQ is 90, then it can be something like this, or something like this on the other side. So these are both two possibilities for the 90-degree angle on this side. And on the other side, we can also have the same thing. We can have something like this, or something like this. Okay, so as you can see here, these are the two possibilities for the 90-degree angle on each of the both sides. And we can see a very common mistake is actually to think that there's only one possibility on each of the sides. But that's actually not the case. Because we can see that this height has to be equal to 3. And if this height has to be equal to 3, then there would actually only be one possibility on each of these sides if it was a 45-45-90 triangle. So if this was a 45-45-90 triangle, there would only be one possibility right in the middle. So we can see that this triangle isn't 45-45-90. Since the base is 8, the height is 3, and in a 45-45-90 triangle, the property is that the altitude is just going to be half of the hypotenuse length. So in this case, 3 is not half of 8. So we know it's not a 45-45-90 triangle. So there's going to be two sides, on the left and on the right, and on the bottom on the top. So there's going to be 4 plus an additional 2 times 2 equals 4 cases. So for an overall sum of 8 cases. So the answer to this problem is 8. So the key thing is that this problem is easy to screw up on, of course, because the way you're supposed to do it is just to go methodically and see that the 3 different cases for the 90-degree angle, count them up, sum them up, and remember that they're not going to be the same point. There's going to be 2 different points here. They're not going to be the same triangle here. Because if it was the same triangle, then it has to be a 45-45-90 triangle. So in this problem here, we have a square EFGH with one vertice on each side of square ABCD. And you have a point E here, such that AE is 7 times EB. What is the ratio of the area EFGH to ABCD? Okay, so let's just say this is 7x, this is x. Let's call this maybe 7x, x, 7x, x, 7x. Okay, so what is the ratio of EFGH to ABCD? To find the ratio of the areas, we need to look at the ratio of sides. So we can see that by the Pythagorean theorem, GH is going to have a length of square root 50x. Since what we do is we do x squared plus 7x squared, which is equal to 50x squared. And the square root of that is square root 50x. And then we can see that the ratio of the area of the blue square to the area of the black square is just going to be equal to square root 50x squared over 8x, since 7x plus x squared, which is equal to 50 over 64, which is 25 over 32. So this probably, you actually need to use x. You could just assume it's equal to 1, and that would also work. So essentially, we've gotten that the ratio is equal to 25 over 32, which is the answer for this problem. Okay, now let's take a look at some more tricky problems. Rectangle ABCD has AB equals 3 and BC equals 4. Point E is the foot of the perpendicular from diagonal B to AC. What is the area of AED? Okay, so notice that in order to solve this problem, we need to somehow find the area of AED. Okay, so what information do we know? We have a right triangle. Let's try to use the information that we have. Well, we know that BE, well, since AB is 3 and BC is 4, we can see that AC will have a length of 5. Right? This will have a length of 5. So then we can see that EB, the length of EB, well, we remember from the property we learned in class, the product of the orange and pink length is equal to the product of 3 and 4. So then we know that EB has a length that's equal to 3 times 4 divided by 5, which is 12 fifths. Right? Okay, so now that we know EB has a length of 12 fifths, now what can we do? So now we can actually see that, well, this triangle here, this blue triangle, similar to the red triangle on the outside. So this blue triangle, ABE, is going to be similar to ACB, the big red triangle. And what is the ratio? Well, since ABC has a ratio of 3 to 4 to 5, it's a 3, 4, 5 triangle, the blue triangle has to also have a ratio of 3 to 4 to 5, the legs. So you can see that AB will have a length of 3/4 times 12 fifths equals 9 fifths. So AE is equal to 9 fifths. And then you can see that AD will have a length of 4. Okay, so now what can we do to find the area of AED? Well, there's actually 2 ways to go from here to use that base and height. So an area of a triangle is 1/2 base times height. So we can do it by just doing 1/2 times the base AD times the height, this green height. Or we can also do it by doing the area of the triangle AD is equal to the base AD times its height here. Right? So what we can notice here is that in order to calculate this area of triangle AED, we just need to find the height from here. So because we already know that AE is equal to 9 fifths. So we need to find the height of the perpendicular here. So what is the height of this perpendicular? Well, to calculate the height of this perpendicular, we can see that, well, the triangles, these 2 triangles are both congruent. ADC is congruent to ABC. So since they're congruent triangles, they're both 3, 4, 5 right triangles. We can see that since the altitude in ABC, the right triangle is 12 fifths, the altitude in ADC, a congruent triangle, is also going to be 12 fifths. So this is going to be 12 fifths too. So if this is 12 fifths, then we can see that the area of ADE is just going to be base, which is 9 fifths, times height, which is 12 fifths, divided by 2, which is 54 over 25. And like I said earlier, there's also another way to use 1/2 base times height. So another way that actually uses trigonometry that I do math mentioned in the comment section is basically that you can also use the 1/2 sine area formula. So we can actually notice that in order to calculate the area of AED, we can use the 1/2 sine area formula. So in order to calculate the area of AED, first we need to find the value of what this angle theta here, the sine of the angle is. Because only if we know the value of the sine of angle DAE, only then we can actually find the area of it. Okay, so what is sine theta? Well, remember, sine is opposite divided by hypotenuse. So sine theta will be equal to 3 over AC, so 3 fifths. Right? Because remember, you can remember it by SOHCAHTOA. So since sine theta is 3/5, now we can now plug it into our 1/2 sine area formula. So we can see the area of AED is just going to be equal to 1/2 4 times AE. And what is AE? Well, we calculated AE to be 9/5. So 1/2 4 times 9/5. So 1/2 4 times 9/5 times sine of theta, which is 3/5. We multiply this whole thing out, and we get 54 over 25 again. So both ways work. The trig solution was really clever, and the half base times height solution was also a great way to solve this problem. Now let's take a look at our next problem. In a regular hexagon, we have A, B, C, D, and we have these points here such that are chosen on sides BC, such that we have these three lengths are all equal. That's what we're given. So if these three lengths are all equal, we're given that they're equally spaced. So these three lengths are equal, and it's also the three lines are parallel, right? So what is the area ratio of area WCX YFZ to the area of the whole hexagon? Well, strategy for finding ratios just assume side lengths are 1, because the ratio will remain constant either way. So 1, 1, 1, 1, 1, 1. Cool. So now, how can we find the area of this middle region here? So we want to find the area of this region here, right? This blue region I just highlighted. So in order to find the area of this region, how can we do it? Well, notice that, let's just call these lengths all maybe 2x, 2x, and 2x. So we can see that each of these individual, if we draw this line here, this part will be x, and this part will be x, right? So now what we can notice is that a very special property about hexagons is you can divide it into 6 equilateral triangles. So we can draw these lines here, and we can divide it into 6 equilateral triangles, right? So these 6 equilateral triangles, what do we know about these 6 equilateral triangles? Well, these 6 equilateral triangles, we know a lot about them, because now we've got parallel lines, and parallel lines mean similar triangles. They generally imply similar triangles. So now, let's try to use the similar triangles properties that we have. So let's just call the area of any one of these equilateral triangles this is the area of any of the equilateral triangles is equal to 9a, right? I'm just doing 9a to make our calculations a little bit easier down the road. So if an equilateral triangle has the area of 9a, so each of these 6 equilateral triangles, then we can see that since the ratio of this to this is 1 to 3, we can see the ratio of the areas of this triangle and this triangle on the outside is going to be 1 to 9. Okay, so we know the ratio is 1 to 3 and 1 to 9. Now what can we do? So you can see that if this is A, this is going to be AA, because the total area is 9A, right? So AA, we can see that the ratio of the smaller equilateral triangle to the bigger one is 1 to 9. Now let's take a look at the equilateral triangle to the left of this. So we can see that this equilateral triangle here, let me just use blue. So this equilateral triangle here, or let's just make it a little bit thicker. This equilateral triangle here. So this equilateral triangle here, notice that, again, this will also have an area of 9a. And since the ratio of this to the whole thing here is 2 to 3, since remember, this length here is 2a, and this is a. So the ratio of this to this is 2 to 1. So the ratio of the areas of AY, let's call this point P, AYP, and AF, let's call this point O, it's going to be 4 to 9. So if the blue equilateral triangle's area of 9a, this will have area of 2/3 squared times 9a, which is equal to 4a. And this trapezoid here will have area of 5a. Okay, so that means this is going to be 5a. The area of this region here is going to be a, and the area of this is going to be 5a. 5a, a, 5a. So the area of this whole middle region, the region we wanted to find in the beginning, this one here, which is going to be equal to 5 plus 5 plus 5 plus 5 plus a plus a, so 22a. So this middle region is 22a. Now what's the area of the whole big hexagon region? The area of the whole big hexagon region is just going to be 54a, because because there's 6 equilateral triangles, each one has an area of 9a. So the ratio of the areas of the middle slit to the overall big hexagon area is just going to be 11/27, the answer to this problem. Okay, so now let's take a look at our next problem. We have in a rectangle AB, BC, and we're given that this is AE is 4, EB is 1, this is 3, this is 1. Because AE is 4, BE is 1, since the total length of AB is 5, BG is 3, GC is 1, since the total length is 4. And we also know DEF is 2, and this is going to be 3, since the overall length of the AB or TC is 5. Okay, so now what can we do? So we can actually notice that we have got a bunch of parallel lines in our rectangle. The opposite sides are parallel. So since we know that the opposite sides are parallel, what can we actually do? Well, like I said earlier, parallel lines typically imply similar triangles, right? So we can see that if you remember from the problem in the previous class, we had a really similar problem where in order to find this length here in the middle, we did 2 pairs of similar triangles and found the ratio and subtracted them. So we can actually try something very similar here. So the thing that we're doing similar here is that to find PQ, we're doing FQ minus FP. We'll actually explore that a little bit later in our similar triangles. Okay, so now let's take a look here. So what immediate obvious similar triangles do we see in the figure right away? Well, the obvious pair of similar triangles is, of course, these 2 pairs. These are obviously similar because the bases are parallel. Very important property of similar triangles. If the bases are parallel, they're similar, and they pass through the same line. Okay, so now we know these are similar. What does that tell us? Well, these are similar. The ratio of the sides is the ratio of the bases, right? So if this is 3x, this will be 4x, this segment here. So we can see that, well, the ratio is going to be 3x to 4x, meaning that PF over QE, PF over QF is going to be equal to 3/7 because 3x to 3x plus 4x is 3/7. So 3x to 4x is 3/7, meaning that if the ratio is going to be 3/7, we're going to actually use this later on, so I'm going to circle this. So now we've extracted length of PF, but we want QP. We want PQ. How can we find PQ? We know PF. Well, we want to find PQ. We know PF. If we find QF, then we can just do QF minus PF, which is PQ. So how can we find QF? Well, given that we found PF using some similar triangle logic, we probably expect that QF will probably be something similar. So in order to calculate QF in a similar way, we need similar triangles. But you might be thinking, QF is not part of any similar triangle. Well, if it's not part of a similar triangle, then let's try to make one out of it. So we can actually extend these 2 lines. And now we've constructed more similar triangles. So by constructing 2 lines, we can see that now we can actually open up new rooms with similar triangles. So now, in order to calculate CG, what do we know about this similar triangle? Let's call this point M. So if this point is M, now let's take a look at some 2 parallel lines here. Okay, now let me erase this. Okay, so what do we know now about our similar triangles from the figure? Well, another cool property is that because we have a line here, we actually know that this pink triangle is going to be similar to the blue triangle on the outside. So since the pink triangle is similar to the blue triangle, we can see that since this is 4, the ratio is 1/4. The scale factor is 1/4. So since the scale factor of these 2 triangles is 4 times, we can see that, well, if this is something like x, then dm will be equal to 2 plus 3 plus x, which will be equal to 4x, because dm is 4 times x. Meaning that 5 plus x is 4x, or that 5 is equal to 3x, meaning x is 5/3. Okay, so if x is 5/3, what can we do? Well, we know x is 5/3. Well, that gives us information about our extended line. So just like I was mentioning earlier, we can now use that in our similar triangles to calculate what the ratio of QFDF will be. So now, if we erase some of these lines, extra lines that we don't need, we can see that the triangles, these two triangles are going to be similar. Okay, so that's useful. That's useful. Now, what do we do from here? We can actually notice that since QF has a length of 3x, now we can look at these two triangles and we know that they're going to be similar. So now we need to find the ratio of QF to EF. How can we do that? Well, we can actually notice that by similar triangles, the ratio of the bases, we can see that AE over AQ is going to be equal to FM, and divided by is going to be equal, since AE over AQ is going to be equal to FM over QF by similar triangles, right? Since the triangles are similar, the bases are parallel, they pass through the same line, they're similar. So now, since we know these properties, we know AE is 4, we know AQ is, well, sorry, I used the wrong information here. I did not mean to say AQ, I meant to say EQ. And that was still true, but does not really give us anything useful. This means to say QF. They're both true. The previous thing I said was also true. It's just that the other thing gives us information about the other side of this, which we don't really care about. So this information, what do we do with this information? Well, if AE is 4, then this tells us 4 over EQ is going to be equal to FM, which is going to be equal to 14/3 over QF. And then from here, we can see that QF over EQ is going to be equal to 14/3 over 4, which is equal to 7/6. So now we know QF to EQ is 7/6, meaning that QF to the overall length is 7 over 13. So we just do 7 over 13 minus 3/7, which is PF to QF. 7 is PF to EF. So we just do 7 over 13 minus 3/7, which is going to be equal to 49 minus 39 over 91, which is 10 over 91, the answer for this problem. Okay, so now we got our answer of 10 over 91. Let's recap the key steps that are involved in this problem. So the key idea was first noticing parallel lines imply similar triangles typically. So we use the similar triangles properties. Then after using the similar triangles, we saw that just like we calculated PF, let's try to also calculate QF. So QF was part of another similar triangle that was outside the triangle. So we extended 2 lines, and then we got even more similar triangles. Then we used properties of the triangles GCM and ADM are similar. Then we found the length of CM from there. And then after that, we looked at all the different properties of the triangles, and we can see that QFM is similar to AEQ. We use that to find the ratio of AEQ to QF, and then also the ratio of PF to EF, and then from there we just subtracted them to find the ratio of PQ. So the key idea was that similar triangles are very useful, and extending lines is powerful to generate new triangles, because triangles are your best friends and easier to work with than other polygons. Now let's explain the meta-solving solution. So there's actually a really cool meta-solving solution. If you haven't already seen the meta-solving video, you should definitely go check that out. It's a great video on how to actually solve problems without solving them. This problem was actually a really great example of it. So I just wanted to demonstrate it here. So if AB is 5 and BC is 4, in the same exact thing we did earlier, well, just like we did earlier in the previous problem, we just use the same pair of similar triangles. We use the same pair of similar triangles. And we see that these two light blue triangles are similar, meaning that PF to EF is 3 to 7. Okay, so 3 to 7. Well, what we can actually see is that since the ratio is 3 to 7, that means the denominator has to be multiple of 7. And then you can actually see from all the choices, I don't have the choices here, but you'd actually see that, oh wait, the choices are here, never mind. So you can see that from all these choices, D is the only choice with a denominator that's a multiple of 7. Because you know that EF is a multiple of 7. So it's likely that out of all these choices, D is probably going to be the answer. So this actually follows the property of looking for the unique properties of numbers. And we know that the only choice with the denominator that's a multiple of 7 is D. So you can go check out the meta-solving video for how to already see that. It's a really cool technique, and you should definitely know it for the upcoming contest. Okay, so thank you all for watching this video. I hope you enjoyed the video. Also, please make sure to like this video and subscribe to the channel for more interesting math competition videos. Also, I hope to see you all next